Yes. Oh, I'm going to say that again. So welcome everybody to this session. This is ASSA session on land use and the emerging policy challenges. This session is completely virtual. So first, let me test whether the technology actually works. So we have 12 participants that I can see in webinars. Can somebody in the audience say maybe I'm here or your name, and so that I just make sure the technology actually works. Just in case you have questions, can somebody in the audience just type a question or anything, say hi to everybody in chat. Okay, so I got a Wednesday Burnett saying hi. Thank you very much. So, okay, we're just going to get the webinar started. Our first speaker is going to be Andrew Rosenberg. Andrew is going to talk about one of the largest agriculture programs, the largest retirement program, conservation reserve program, and its land use and water quality impact. Andrew, now it's your turn.
Okay, I think let me do full screen with this. Okay, can everybody see all right? Okay, so I will be talking about land use impacts of the CRP. This is a project that's co-authored with Brian Pratt and David Arnold, and we're all at the USDA Economic Research Service. So CRP is the largest land retirement program in the US. It's administered by USDA's Farm Service Agency. And it's made up of three main components. So probably the best well-known is the general sign-up of CRP, which is an auction and is the focus of this particular study. But also it's worth discussing the other two main parts of CRP. So there's continuous sign-up, which is not an auction, which is available on a continuous basis, as the name suggests. And actually, even though it's less acreage overall, it comprises a bigger part of the budget for CRP. And then finally, there's grassland CRP, which is a pretty big amount of acreage, but not so much in terms of overall rental payments. So why am I interested in land use and CRP? Well, it's a land retirement program. This is the main mechanism through which the CRP tries to obtain certain goals. So I've listed the main objectives of the CRP, and each of these are influenced by the intensity of land uses that are retired through the program. So it's important what the program actually does in terms of land use. And then finally, we're interested in the relationship between land use impacts and program size. So there's been some recent proposals to increase the acreage amount in the CRP. So we try to get some sense of the relationship between the size of the program in terms of acreage and what the land use impacts are. So I've kind of gone over these three main questions. What are the overall land use impacts? We also try to get a sense of how much does it cost to retire different types of land in the CRP? And then we look at the influence of program size. So in this slide, I give an overview of general sign-up CRP, which again is the main focus of this study. So basically what this comprises is a landowner offers a parcel of land. If they're accepted into the program, they have to grow an approved land cover for 10 years instead of some commodity crop. And in return, they receive 10 years of rental payments and a cost share for the land cover that they establish as part of the program. There are a few different eligibility requirements. So this includes having highly erodible land or being within a conservation priority area. They also have certain crop history requirements, so 4 years of a certain specified 6. And so we focus on the 2016 sign up in this study. So that was 4 years from 2008 to 2013. Or if they are in the last year of a CRP contract, or if there's a gap in between different general signups, people with expiring CRP land can also qualify. So an offer is composed of a few components. First is what we can think of as the exogenous component of the offer, which is basically an estimate of how environmentally sensitive the parcels that are offered are. And then there are 2 parts that are actually offered from the landowner. This includes a rental rate, which is in part is based on the county average rental rate of the parcel, and also a productivity factor, but is also based on how much the landowner offers below that maximum rental rate that is given to them. And then another part of the offer is a particular land use that they grow on the land that's being retired. And so if you take all these things together, there's a formula that creates what's called the Environmental Benefits Index. And once everybody makes an offer, the Environmental Benefits Index scores are ranked, and any offers that are above a certain determined threshold are accepted into the program, and any offers that are below that threshold are rejected. So in 2016, which we look at, this actually had a historically high EBI threshold, so there were a lot of rejected offers. And as I'll explain in a little bit, that's part of the reason that we use 2016, because we look at rejected offers in particular. So there has been a decent amount of work on this relationship between CRP and, sorry, yeah.
Could you pause in the previous slide? So first of all, for live audience, attendees, you can raise your hand, you hover over your name and unmute, and then I can unmute you and to ask a live question. So if you can, so if anybody in the audience has a question, so you can just raise your hand just in case you have clarification questions. For example, I do have one here. You said eligibility. In the first, I thought it's 10 years. Is it, what's exactly the length of history required to be eligible for CRP? Here you say it's from 2008 to 2013. I thought it's longer than that.
For this particular, it does vary from sign up to sign up, but for this particular year, it was 4 of the 6 years from 2008 to 2013.
Just for this particular sign up?
Yes.
Okay, thank you. Thank you.
So this relationship between CRP and land use has been looked at before in the literature. Most studies that look at this have focused on exiting CRP land or land that was previously in CRP before looking at their land use. The results are fairly consistent across these studies. They've tended to find that about 60% of that land goes back into crops. Some other studies have looked at an actual average treatment effect on the treated, but the results have been pretty similar, around 60%. But there have been some other studies that have suggested that there might be some differences among different subpopulations. So there might be a higher impact in early years of CRP enrollment. And also there could be differences between people that are exiting voluntarily, so they choose not to make an offer after exiting the CRP, and people that make an offer and are rejected. So there's been a recent study that showed that if you compare these two groups, people that were rejected are much less likely to go back into crops. So what do we do differently from this previous literature? Basically, what we do differently is all related to the fact that we look at rejected CRP offers, and again, from the 2016 sign-up. This allows us to look at both farmers that are newly enrolling into CRP or attempting to enroll, and land that was previously in CRP. it also allows us to link the information from the offers with the land use that they subsequently do, so that we're able to see how much it costs to retire certain land. So we'll get into some more details about how we do that. But basically, if rejected offers were instead accepted, looking at what they do after being rejected gives us some sense of the land use impacts, and then we can link that with the proposed rental rates, which gives us some sense of how much it would cost. And then we also have information on what their EVI scores were. And so we can see if the program was expanded a little bit, how do the land use impacts and the cost vary as the EVI threshold is decreased. And then finally, we're able to look at different subpopulations. So we kind of speak to the literature in this way. We look at voluntary versus involuntary exits. And then we also look at new and existing CRP land that has rejected offers. So last background slide, just a deeper look at the data. As I've said a couple of times, we do look at the 2016 general signup. And this is particularly of interest because fewer than 20% of the offers were accepted. We do focus on states in the Great Plains and Midwest regions, and this comprises the great majority of offers. And then of those offers, 93% have some geolocating information. So once we kind of narrow down the set of offers and we link that to fields, we have about 24,000 fields to analyze that are associated with rejected offers. And again, this includes information about the proposed land covers that they would have done if they were accepted into the program, what they would have been paid in terms of rental rates, and what their EVI scores would have been. And then also, because this is geolocated, we can link this to land use data through the what's called the Common Land Unit data set, which identifies the particular field that the fields that these offers were on. So the land use information is from what's called the 578 form data, and farmers report what they're doing with the particular parcels. So this includes a few different categories: cropland harvested for grain, harvested for forage. It also includes grazing land, and then what we call other. We actually split out left standing and then another one called other. And then it also identifies whether a parcel was in CRP. And sorry, this land use information is from 2013 to 2019 for all fields. Okay, so now we're going to get into the analysis. I'm going to start with the land use impacts of rejected, the land use impacts the CRP, and doing this by looking at the land use decisions of rejected offers after the 2016 sign up from 2017 through 2019. So this is split up. So this figure shows the proportions of rejected offer fields that are in each category of land use, and it's split up by quartiles of EBI points for the rejected offers. So for the first quartile, that is the quartile with the highest EBI points. And if the program was to expand a little bit, it would accept these parcels first. So what you can see is that the amount of land in grain and forage is about 58% for this first group, and the remaining amounts in grazing, other use, and then about 18% ends up going into CRP through continuous signup. And then these results are fairly constant as you go down in terms of the EBI. For the fourth EBI quartile, it's actually quite a bit higher for the amount that's in grain and forage. So if the program was to expand a lot, the land use intensity would, the land use intensity of the land that would be retired would increase. In this next slide, it's a very similar thing that we're looking at, but we exclude the the land that goes back into CRP through continuous. And this way you can see, you can kind of get a better idea of the land that's being retired, how much of that is avoided grain or forage, et cetera. So when you do that, you can see in that first quartile, we have about 70% of land that's in some sort of croplands or grain or forage. And then that increases as you go through the quartiles. And then in this slide, I'm actually going to skip to this next slide. So this is looking at the land use impacts across state, and it excludes land that goes back into CRP through continuous. So what you can see here is that there's quite a bit of variation. The states with the highest amount going into grain tend to be the states with the most land in grain, so the Corn Belt states. And then you can see land with less land in grain are also not that surprising. Nebraska, Montana, a very small amount, and Wyoming, only 2%. So when we look at cost, these differences across the states are going to be quite different. But it's worth keeping this in mind when we see that slide later. Okay. So I mentioned a couple times that there might be differences among subpopulations, and in order to look at this, what we do is we take all of the rejected offers from the 2016 sign up and match them with unoffered fields based on a few different characteristics. So land uses previous to the sign up, NCCPI, which is it's a crop productivity index, highly erodible land designation. This sample includes about 6 million fields. And then using the sample, we test the outcomes of different land uses in terms of proportion of each of the land uses I've been discussing. We test how different combinations of previous CRP status and offer status predict these land uses. So if this is confusing at all, it'll be more clear when I look at the next slide. So I'm just going to focus on the first column here. What you can see is there's a pretty significant negative impact on the proportion of land that is in grain after 2016 for the groups that were previously in CRP. And so what this suggests, and this doesn't differ for land that made an offer and for land that did not make an offer. So what this suggests is that there seem to be persistent effects of the CRP on not having not being an intensive land. And so if you look at column 5, this supports this idea, because what we see is that there's a significant positive effect for both of these groups for left standing. So left standing can be thought of as very similar to what CRP would be, basically some sort of grass that's not harvested. And we see a much higher proportion of land that previously was in CRP ending up in left standing. So this suggests that people are continuing to have an unproductive use for their lands after exiting. And it doesn't have to do with, at least in our sample, it's consistent across people that made an offer and that did not, although it does appear to be a little larger for those that made an offer. Okay, so the final part that we're going to look at is the cost of enrolling land. Basically, how much do you get for what you pay for? So the way that we look at this is we take all the rejected offers and we imagine that if instead of being rejected, they were accepted into the program, how much would it cost to get a certain acreage of each land use? So put another way, how much grain would you get? How much cropland for forage, grazing, et cetera, would you get for every $100 additionally that you could have spent on the CRP? So again, we look at this across EBI quartiles. So just focusing on this first quartile, if $100 was spent on enrolling these offers from the first quartile, what would be obtained would be 0.92 acres of grain, 0.29 acres of forage, and then 0.29 of both grazing and other use. This measure of cost effectiveness in terms of acreage actually increases a little bit when you go to the second quartile. And in general, across these first three quartiles is fairly constant, and then drops off quite a bit in the fourth quartile. And the reason that cost effectiveness goes down is because the rental rates are going up as you go across the quartiles. So eventually these higher rental rates have quite a bit of an impact on cost effectiveness, but perhaps somewhat surprisingly, not until you get to that fourth quartile. So again, we look at variation across state. And what's kind of interesting is that when you look at cost effectiveness, the states with the most grain or forage per $100 spent are considerably different from what we found for proportion of grain and forage overall. So if you remember, we saw that states like Illinois and Iowa and Indiana had very high proportions that of retired land that were in grain and forage. But now that we're accounting for cost, we see the most cost effective are states like Montana and North Dakota. And the reason is that these states have much lower rental rates. So there's a trade-off between how much grain and forage is being grown on this land and what the rental rates are. And when you combine those, these states are the most cost effective. So in summary, we find that excluding land that goes back into CRP through continuous, we find that of the rejected offers, 60% went into grain, 15% went into forage. About 20% of the rejected land did go back into CRP through continuous. We do find that the land uses avoided are fairly steady, but the amount in grain and forage does increase a bit as the EBI decreases. And then we did find that for land that was previously in CRP, they were less likely to go into grain in the years after the sign-up. And then looking at cost effectiveness, we saw that across the first three highest EBI quartiles of the rejected offers, about 1.2 to 1.3 acres of forage and grain were retired per $100 that could have been paid in accepting these people, these parcels. And so again, we find that it's fairly steady cost effectiveness across those three first quartiles and then drops off in that fourth quartile. And then finally, we do find that there's quite a bit of variation across states. Okay, so that's all I have. I think we probably have a couple minutes, but also happy to answer questions in the chat or wait until the end.
Yeah, we have a couple minutes for questions. For the audience, if you have questions, you can raise your hand and then I can unmute you. Or you can just type your question in the chat window.
I guess I'll ask a quick question.
Yeah, go ahead.
Andrew, I'm not really familiar with CRP. So with the EBI, it's Environmental Benefit Index, do you know if that's correlated with land productivity?
I'm sorry, I didn't catch the last. With what kind of activity?
Do you know if EBI index, if that's correlated with the land productivity?
So the EBI does have, so if you have a higher average rental rate in your county, then that actually decreases the EBI, all things constant. Is that what you're asking?
That's interesting. Somewhat, but Environmental Benefit Index, that's like how much you save like in nitrogen runoff or something like that, right? That's what probably refers to.
That's part of it. that's definitely part of it. So it's not clear that there's not an obvious relation. I think you mentioned productivity. We have looked at relationship between productivity and the kind of environmental portion of EBI and have not found much of a relationship. I think it's possible that there's a relationship after you, if you only look at those that made an offer, because people with high amounts of what we're calling environmental sensitivity, the land that has higher amounts of environmental sensitivity has a high EBI score to begin with. And so they're more likely to make an offer. And so if you have really productive land and you also have high environmental sensitivity, you might be less likely to make an offer than if you have less productive land and higher environmental sensitivity. So there might be a correlation because of that.
Yeah, that's where I was going.
Ruking, did you have a question?
Just a very quick question. It is a little bit surprising to me to see nearly 20% of land got rejected, enters continuous CRP very soon. You mentioned earlier on the continuous CRP has higher environmental requirement, and pays more. So I think that turns out a better thing for those rejected offers.
Yeah, I mean, it's an interesting question that definitely needs some looking into. We haven't looked at it all that much. What determines who goes into continuous or who doesn't? But there's definitely that trade-off. I think, as you alluded to, you get a higher payment in continuous, but there are higher requirements. So it is interesting that 20% decided that that was a good. That I guess it implies that general CRP was a better decision for them, but after being rejected, they decided that continuous was better than whatever the alternative was.
Other questions from the audience? If not, we're going to move on, but you can always write down your questions, and we'll have some time for Q&A at the end of the full presentations.
I think there's something in the chat. I don't know if we have any more time to answer questions, or I'm happy to answer it in the chat also.
Yeah, I think it's Dave Derist, a website. Okay. Yeah, we can always come back for more discussions afterwards. Is that okay? Yeah. So we're going to move on to the second presentation. Our second presenter is Yue. Yue is going to talk about unconventional oil and gas and related land uses. And I'll let Yue take over then. So actually, before that, Levin is a co-author of this presentation, and I'm only the moderator. Levin put all of the effort to organize this session. I should have acknowledged that at the very beginning. It's just how ASSA runs this, how to let the meeting flow. I'm just happen to be here to monitor the flow, but Levin did the work. Thanks.
Can everyone see my screen? Can everyone see my screen? Okay, great. Good afternoon, everyone. I'm Yue Lu, a postdoc from the Department of Resource Economics and Management at West Virginia University. Currently, I'm on the job market. The work I'm going to present today is unconventional oil and gas development and agricultural land use in the US. This work is co-authored with Levin. He is an associate professor from the same department as mine, and Shelley. She is an associate professor at Department of Agriculture, Economics, and Rural Sociology at University of Idaho. This work aims to explore the relationship between recent rapid UOG development and agricultural land use in the contiguous US and several major shale play regions. I will introduce the motivation of this study first, followed by the method and data, results, and the discussion, and the conclusion. Since the US shale revolution began in 2008, the use of horizontal drilling with high volume hydraulic fracturing has become highly prevalent. This technology enables US energy producers to extract oil and gas from unconventional sources in a cost-efficient manner. This figure here shows that the number of active UOG wells grew more than tenfold between 2005 and 2018. Energy market growth and the development of UOG can affect agricultural land use in both positive and negative ways. First, UOG development competes for land with the agricultural sector. The development of UOG may displace agricultural land because developing a new site for drilling requires corresponding infrastructure, such as new roads for access, well paths for drilling, and pipelines for shipment. Second, UOG and agriculture to some degree compete for factors of production, such as water and labor. Third, increased oil and gas supply and its associated decline in energy-related import prices in agricultural production could encourage expansion in crop acreage. And fourth, the UOG development generates capital gains, including land appreciation and the revenues from royalties. Capital gains, on one hand, may be used to invest in machinery, upgrade technology, or obtain land to expand crop acreage. On the other hand, this windfall income may encourage earlier retirement of farmers. So overall, the net impact of UOG development on agricultural land use is ambiguous. So the goal of this study is to explore the net impact of UOG development on agricultural land use in the US. This study contributed to previous literature by following aspects. First, we expand the study area to the contiguous US and compare the results from several major shale play regions. The major shale play regions include Appalachia. The Southwest includes the shale plays in the Arkansas, Louisiana, New Mexico, Oklahoma, and Texas. And the Great Plains includes shale plays in the North Dakota, Montana, Colorado, Wyoming, and Kansas. We also explicitly considered the effect of the structural change in the energy market break in 2008. And also, different from previous literature, we considered the quadratic specification to account for a potential nonlinear relationship between regional UOG development and agricultural land use. The nonlinear relationship may occur because the initial UOG development can have a larger marginal effect on such as infrastructure construction than the subsequent new wells. To solve the research question, the empirical strategy is based on county-level analysis that assures data availability, including land use change, UOG development, climate variables, input and output prices across multiple regions. There are a total of 5 specifications applied to examine the impacts of UOG production on agricultural land use. The first model examined the linear relationship. The dependent variable is the aggregate annual crop acreage in County I at time t. Independent variables include the lead output price, climate variables, fertilizer prices, time trends, and the UOG development level in County I at time t. We also control the unobserved county level time invariant effects. The second specification includes both linear and quadratic terms to allow the marginal effect of additional UOG development. And the third one investigates the marginal effects of UOG development on crop acreage before and after the breakpoint of energy markets, the year 2008. The fourth specification examines the difference of crop acreage in counties with and without UOG after 2008. And the last one investigates how crop acreage change when a county begins to produce UOG. So in addition to using the full sample data or county, we also estimate equation 1 to 3 using the subsample of only the counties with UOG production. The econometric analysis is based on a balanced panel of annual observations from 2,612 counties in the US from 1997 to 2018. The dependent variable is the aggregate crop acreage of 8 major crops, including barley, corn, cotton, oats, peanuts, rice, soybeans, and sorghum. 1 year lagged last period's price index is used as a proxy for the crop price. Climate variables include the annual average precipitation and the temperature at the county level. For the fertilizer costs, we use the National Index of Fertilizer Prices from USDA ERS. For the level of UOG development, we measure it using the number of active UOG wells. Both oil and gas wells are included in the analysis. The well data obtained from Emerald, formerly known as Drilling Info. Here is the summary statistics. Heterogeneity in crop production and UOG development across regions are evident. The average county level crop acreage is the highest in the Great Plains, followed by the Appalachia and the Southwest. Meanwhile, 60% of counties in Southwest have had at least one active UOG well during the sample period. It is the highest across 3 regions. Of the counties with UOG development, the average number of UOG wells is 41 in Appalachia, 93 in Southwest, and 86 for Great Plains. This table presents the estimation results for the contiguous US. The left part is the results for the full sample. Each column corresponds to each specification, and the right part is for the subsample. Each column corresponds to the linear effect, quadratic effect, and the effect before and after 2008. So results show that the UOG development on average negatively affected the aggregate acreage in the US during the sample period. There is no quadratic effect. The UOG development after 2008 significantly affect crop acreage. On average, a county with UOG development after 2008 reduced the crop acreage by around 4,600 acres. For the Appalachia region, the UOG development affects agricultural land use negatively and linearly. Other impacts are statistically insignificant. This finding is consistent with previous literature, which found that there was little change in total farmland acres in drilling relative to non-drilling counties in this region. Our possible explanation is that most agricultural counties in Appalachia do not have the UOG resources. The shale play is largely located beneath the Allegheny Plateau with lower productivity soil. For the southwestern region, none of the impacts is statistically significant for the 4 samples. Since oil and gas production in the southwest has a much longer history than in other regions, counties without UOG production in this region may not have the access to the UOG resources in their nature. So the use of the 4 sample, which includes both counties with and without active UOG wells, could dilute the impacts of UOG development on crop acreage, resulting in these insignificant coefficient estimation. The estimation results using the subsample here shows that the number of active UOG wells positively affects the crop acreage in counties with UOG production in the southwestern region. I will discuss this positive relationship in detail later. The estimation results for Great Plains show that UOG development overall negatively affects crop acreage. The quadratic terms are significant in both cases, suggesting the negative effects of UOG development on crop acreage is diminishing. In addition, a county with UOG development has around 13,000 acres less cropland than other counties after 2008. The results presented indicate that the effects of UOG development on county crop acreage vary by region in terms of both size and magnitudes. In Appalachia, the negative effects such as the infrastructure development and windfall income from UOG production dominate the positive effects, leading to the reduced crop acreage. This could be driven by 2 reasons. First, the Appalachia region has a relatively short history of UOG development, which requires high level of infrastructure construction. Second, previous literature reported that UOG development resulted in greater land appreciation in Appalachia, and more farmers in this region own mineral rights. So high windfall income in Appalachia may discourage agricultural production instead of supporting the reinvestment in crop acreage expansion. Similar to Appalachia, the Great Plains began to produce UOG in recent 15 years. The demand of UOG associated infrastructure is high, which results in the negative relationship. But with more drilling activities, the additional wells require marginally less land. The results for Southwest are different from other regions. We find a positive relationship between the number of active UOG wells and the crop acreage. And 2 factors may help explain why the results for Southwest differ from other regions. First, compared with Appalachia, the split estates means that different parties own surface and underground mineral rights are more common in Southwest. Also, previous literature document modest land appreciation in this region relative to the Appalachia. So the limited capital gains may have encouraged farmers expand crop acreage in Southwest instead of early retirement. Second, the Southwestern region has a longer history of oil and gas production than other regions. Recent UOG production growth in this region has required relatively less additional infrastructure, as they had already been in place and used. In this study, we provide an analysis of how UOG development affects agricultural land use in the contiguous US and the 3 major shale play regions. Our results highlight that policies concerning the agricultural land use change due to UOG development need to be region-specific and account for the possible nonlinearities. Several limitations of this study should be mentioned. First, the decision-making regarding the crop acreage is complex, and our findings could be transitory with the rapid development in energy and crop markets. Second, due to the use of county-level data, we are unable to identify some important farm-level characteristics such as oil and gas right ownership, lease, and royalty payments. Third, although we include various control variables in the analysis, we are unable to account for many other factors that also affect crop acreage at the county level. For example, farmer risk preference of crop production. As long as these variables are uncorrelated with the key explanatory variable, the UOG variables, the coefficient estimation results for UOG variables should be consistent. And finally, we investigate the impact of UOG development on crop acreage using the number of active UOG wells, and do not account for permitted but inactive wells. Permitted but inactive wells include wells that have not yet been drilled and wells that have been drilled but have not been fractured. The number of drilled but unfractured UOG wells has been growing in recent years in the US. These wells may occupy land in terms of the infrastructure preparation. So the inclusion of drilled and undrilled permitted wells may uncover a larger effect of UOG development on agricultural acreage than observed in this study. We use the number of active UOG wells. So future research should consider the impact of these well permitting on land use. So thanks for joining my presentation. Questions and comments are welcome.
There's a question in the chat window. Yellow, can you see it, or you want me to read it?
Yes, I can see it.
Okay, everybody can see it. David has a question. David Bulan has a question in the chat window.
For David's question, I didn't check the effect of the provide water wells for electric. I didn't check this effect. Thanks for mentioning it.
Are you considering the second question?
Yes, I'm reading the second question. Column 5 does not. Yeah, the well dumping, the UOG well dumping is initially significant when we cross the arrow at the county level. But when we cross the arrow at the agricultural statistics district level, this estimation becomes too insignificant. So we will further check
You check. Okay.
Yes, I will check.
I think Justin has a question. Go ahead, Justin.
Thank you so much. This is actually just a comment kind of following on David's point or question. So in parts of the Southwest region where you're getting this interesting result, UOG and crop production are actually complementary in that there's a history, in particular in California, of using oil field produced water as a substitute irrigation source in crop production. And so you might dive into that a little bit more in your discussion around use of water from oil and gas operations to help support local irrigation systems.
So the produced water from the UOG production will be a water resource for irrigation, you mean?
That's right.
But this produced water is usually toxic water.
It can be.
Right?
It can be. It's certainly of lower quality than most irrigation sources. And there's an emerging literature in the environmental science space that is exploring the relative toxicity or the implications for food safety of using oil field produced water.
I see. Thank you for mentioning that.
Any other quick question from the audience? If not, now we'll move on, but later on, if you have questions, you can ask during the Q&A sessions after the first presentation. So we're going to move on to the third presentation of this session. It's going to be Justin Ism. So Justin is going to present something I think that's different from the first and second presentation. More specifically, it's about how national sustainability climate goals may interact with land use, basically, land use projections. Go ahead, Justin.
Sorry, I accidentally muted myself momentarily. All right, well, thank you all for sticking with this late Saturday afternoon. I appreciate it, and thank you very much to Lavon for organizing and to Hongli for moderating this session. It's great to see you all. So I changed my title up a little bit. I'm sorry about that. I do this sometimes, but the focus is the same. What I'm going to present today is part of a broader effort to explore land use sensitivities or to develop sustainable land use projections in the United States under a wide range of climate and sustainability-oriented policies. What I'm going to talk about today is a subset of that work. We're going to focus on healthier diets and agricultural productivity growth assumptions in the US. All right, so moving on here. Great, so what's the motivation? So part of what we're trying to do with this collaboration and building sustainable land use pathways, not just in the US, but in other countries of the world and globally, relates to the Sustainable Development Goals put forward by the United Nations. And the point that I want to make with this slide is, regardless of whether we're talking about SDG 1, no poverty, SDG 2, zero hunger, or other SDGs, life on land, affordable and clean energy, the connections to the land use sector between Sustainable Development Goals and land as a primary resource base or primary input into these systems is really critical. And it's maybe been, I would say, underappreciated in previous assessments. Second, if we look at current climate stabilization projections from the integrated assessment modeling community, be those sort of national projections and national climate action strategies out of the US and other regions, or big global studies of how we achieve net zero or stay on course to hit a 1.5 degree stabilization pathway, land is a really critical input. It's a critical input both to reduce greenhouse gas emissions through increased carbon sequestration. It's an important input into the energy system as a source of bioenergy feedstocks used in negative emissions technologies. It's a really critical resource in how we adapt to climate change. And of course, among this policy backdrop, there's growing challenges. We have a growing population, which is demanding more food, fiber, and energy. We have major concerns about rapid biodiversity loss. There's been a lot of popular media about this recently, and the need to really set aside remaining land resources where natural processes predominate. And then, of course, environmental change, which could be gradual, as we're seeing with climate change, or more rapid. You know, in the East Coast of the United States right now, we're experiencing some rapid ecosystem change in the form of ghost forests, which are, you know, showing this kind of rapid this rapid change from forest ecosystems into marshlands. Okay, so this work recognizes that, you know, regardless of what kind of policy we're thinking about, right now in the land use sectors, we're really facing a confluence of potentially competing policy objectives. Separate policies we know can shift resource demands, right? If we're setting aside land for conservation purposes to help protect biodiversity, that's going to reduce the amount of land that we have available for development or for agricultural production or for other primary productive uses. We know that if we're pursuing climate change mitigation opportunities, that also has a potential trade-off in our production systems, right? So there is a kind of constant push and pull between the resource demands that each of these policies have independently. And so one of the things that we're sort of interested in longer term is understanding the confluence. Whenever we throw everything at the land use sectors, what does it mean in terms of our primary production systems? What does it mean in terms of environmental outputs? Today, I'm going to focus on the box in the upper right-hand corner, and that's really related to food security, health, and nutrition. Just really quickly, the U.S. policy landscape. Some of the motivating things that have come out recently supporting this work. One is the White House long-term strategy for decarbonization, which presents potential pathways that the U.S. might take to help get to 2050 net zero target that the Biden administration has laid out recently. And, you know, the point that I wanted to make here is some of the major components of these pathways: decarbonizing electricity, non-CO2 emissions reductions, increasing the land carbon sink, and CO2 removals, such as CCS technologies. The land use sectors are going to play a really important role in achieving these ambitious climate targets in the US. Other policies, we've heard about one major initiative already. So we're looking at a continuation of federal conservation programs like CRP and EQIP and others. There's also a newly announced about a year ago agriculture innovation initiative through USDA, and this sets really ambitious environmental targets, including a 30% reduction in nutrient loss over the next 30 years, a 50% reduction in food waste, general goals of increasing agricultural productivity, some of which are commodity specific, and expanding soil carbon sequestration in US agricultural systems. Simultaneously, the focus of this talk are the US Healthy Diet Guidelines. And so here, these are policies, if implemented, that could potentially help us see a more rapid transition to healthier diets, reducing, in particular, red meat consumption in the US, to alternative sources of protein, and to a higher proportion of calories from fresh produce, from healthier grains. And these are, if we do see a transition to healthier diets, this of course could have pretty dramatic implications for agricultural production in particular and agricultural land use, and we'll get into that momentarily. And then of course, continuing to drive demand for land are biofuels, bioenergy oriented policies, and now increasingly other renewables, so solar panels and wind energy. Okay, so why healthier diets? So from an economic perspective, we care about healthier diets because a shift to a diet, a diet that has a lower proportion of red meats, shifts to alternative proteins, shifts to a higher proportion of healthier produce, reduces the disease burden in the US. right? About 20% of the deaths in this country are attributable to dietary risks. And this, of course, leads to heart disease, among other morbidity implications. But also increasingly, the literature has turned to evaluating the potential environmental benefits of healthier diets, right? So this is a figure taken from the Eat Lancet report that came out in 2019. And I don't want to spend a lot of time here, but basically they look at a serving size of different types of food. So ruminant meat or red meat at the top, pork, chicken, fish, all the way down to fruits and cereals. And you can look at the relative environmental impact in terms of greenhouse gas emissions, the land use required to get to that serving, the energy use required to get to that serving, the acidification potential, and the eutrophication potential due to the nutrients and the fertilizer required to get that serving of food. So obviously, shifting away, well, the point being made here in this kind of life cycle approach is that shifting away from a meat-intensive diet would help you to reduce the environmental burden of the food system, and hence give you this indirect source of mitigation. Okay, so our objectives in this paper is to evaluate whether US healthier diet transitions and productivity growth, thinking about supply side policies that boost agricultural productivity, can complement sustainability and climate goals. And by complement, I mean, do they provide direct greenhouse gas mitigation benefits? And do they help free up land for alternative conservation initiatives? And then we explore interactions between both these demand and supply side policies. And we look at policies that are implemented in isolation just in the US versus globally defined diet transitions. Our approach, we use a multi-model global simulation analysis of these alternative diet and productivity growth scenarios. Our contributions here, we make the case that empirical techniques are not always well suited to evaluate new policies or multi-decadal time horizons. We move a little bit beyond some of the recent literature in the US modeling context, which is either focused on scenario narratives using integrated assessment models or multi-sector partial equilibrium approaches, or climate change impacts in the agricultural system, or really direct climate policy incentives such as carbon pricing or bioenergy expansion incentives. And finally, we make the case that dietary transitions have been largely ignored in the US economic modeling literature, especially recently. And some of the recent published assessments are global in scope and may lack national perspective. Okay. Very briefly, because there's a lot of literature out there on these models, and in particular, the model on the left-hand side here, the Global Biosphere Management Model. This is principally developed by colleagues at the International Institute for Applied Systems Analysis. This is a multi-sector partial equilibrium spatial allocation model of land use, so forestry, agriculture, and bioenergy systems. The model is recursive, dynamic, and solves for economic surplus under future economic conditions, including policy change, socioeconomic drivers, such as income growth, and environmental change. We're able to capture both national and global market feedback through trade flows and through connections between markets and resource systems. The second model that we use is what I call the FABLE calculator. So FABLE stands for Food, Agriculture, Biodiversity, Land Use, and Energy. There is a link here for anyone interested in learning a bit more about the FABLE consortium. This is a spreadsheet-based model. It is an equilibrium displacement model that's clearing markets and maintaining mass balance in the land use system and allocating land according to economic rules that are exogenously defined. It captures connections between production systems, land use, and in the environment. And it's used currently to facilitate multi-country iterative analysis around sustainable land use pathways. It also allows us to conduct rapid assessment or rapid sensitivity analysis of different land use projections, where we say maybe we want to look at the implications of adjusting a key parameter, or we want to recalibrate trade flows in an iterative fashion. Okay, so the modeling approach here, I'm going to present a business as usual scenario, which is based on income growth projections globally and regionally from the shared socioeconomic pathway SSP2. That's commonly thought of as a business as usual or middle of the road scenario. US and global diets are consistent with current consumption trends, right? So if you look at the figure on the right-hand side, this shows our current trends out in 2050. And here you see a very high proportion of caloric intake from red meats, from sugar, from poultry and eggs, all of the things that the healthier diet guidelines established by the USDA would have us cut down on. Alternatively, our sensitivity scenarios here look at a few alternative futures where we're pursuing, for instance, healthier diets in the US. In those healthier diets, you can see that composition change dramatically. We're seeing a larger proportion from roots, from vegetables, from nuts, while we see dramatic reduction in poultry, red meats, pork, and vegetables and oil seeds. In addition to just considering healthy diets, we look at alternative scenarios. We're looking at healthy diets in the US only, healthy diets in the US plus high productivity growth and crop production, so high yields. We look at healthy diets in the rest of the world, so a similar healthy diet transition applied globally, healthy diets in the US and the rest of the world, and a sustainability scenario. And that sustainability scenario basically throws everything in there together. So healthy diets globally, high productivity growth in the US. Okay. The reason we link multiple models here, we can use a model like GloBiome just fine to present these alternative future projections, but the calculator allows us to provide variability bounds and run additional sensitivity scenarios around key input parameters. And so here we focus on additional sensitivity analysis related to livestock production intensity. So in particular, looking at the parameter related to beef productivity, which is an endogenous variable in the GloBiome model. And that gives us a metric of the amount of livestock production per unit area, or I'm sorry, per unit animal, as well as ruminant density, which gives us total livestock units per unit area. Then we can use that to get a metric that we call beef land use efficiency, which is 1,000 tons of beef output per unit area. So this allows us to sort of rapidly take endogenous projections from the GloBiome model, calibrate all of the production and land use trends that we see from the model to this calculator tool for expanded sensitivity analysis around these key productivity parameters in the livestock sector. And that's kind of what we're showing here is those variability bounds around those calculator inputs relative to the trends that we're projecting within the GloBiome model. So just really quickly on some production results, we find that meat and feed grain production declined substantially, consistent with our diet assumptions, right? So in particular, beef declines by about 50%, chicken and chicken and pork production also declined by about 2/3, consistent with the diet guidelines. We see that crop production impacts, though, they're a little bit different. They're mixed, right? So we see a pretty dramatic drop in corn production, mostly due to reduced demand for livestock feed. But we see increases across most of our scenarios for soybeans and for wheat. The soybean results are a little bit interesting. We do see a decline in demand for oil seeds overall, but we see in particular under these higher productivity scenarios, growing foreign demand for US produced goods. And so that increases the amount of soybeans that we're producing. Yields, the change in yields that we project varies considerably crop to crop. In general, we see, of course, the highest productivity growth rates where we're exogenously telling the model to meet higher yields. But in general, we see that there's a counteracting force here where healthier diets reduce relative crop rents, and we see a lower endogenous yield response. And so you can start to see a tapering off of yields for a lot of commodities in our projections under our healthy diet scenarios. Some quick results on projected land use. There's a pretty wide range that we find across both our GloBiome and our calculator results in terms of the net change in land use. In general, under our healthier diet scenarios in particular, we see a reduction in total cropland area ranging 2 to 4 million hectares just in the US. The most dramatic impact is on pasture land use for grazing, for cattle grazing. There we see a reduction in approximately 25 million hectares by mid-century, consistent with these healthier diet scenarios and the reduction in the demand for pasture lands in the livestock system. This corresponds to about a 30 million hectare increase in lands where natural processes predominate, so grasslands and forests. What does that mean for the resulting greenhouse gas emissions profile of the system? So what we show is that healthier diets reduce livestock emissions by about 75 million metric tons. That's roughly a third of our the emissions from the livestock sector under current conditions. We see that this increase in natural area shows an increase in carbon sequestration from natural forests or from grasslands, and so we do get this additional mitigation benefit just from land use change. But ultimately, what we find that was at least a little bit surprising to me is that these emissions results are extremely sensitive to these livestock productivity parameters, right? So the net change, this indirect change in land use change CO2 emissions resulting from our healthier diet scenarios are really complemented by or potentially very complemented by policies or investments that would improve livestock productivity or improve livestock sector intensity. So I'm not sure how I'm doing on time here, if I need to slow down or not, but maybe I'll just push through. So here are some key takeaways. So our healthier diet scenarios that we've run here.
You can have a couple more minutes, Justin.
I'm sorry?
You can have a couple more minutes.
Wonderful. Okay. So what we find is that our healthier diet scenarios show to be complementary with climate and sustainability goals. And they're really complementary in a couple ways, right? So we show very directly that you get mitigation benefits from shifting to an agricultural or a food production system that is less meat intensive, less livestock intensive, and reduces the amount of feed grains being produced. So although we see a relatively small change in cropland area, we see major benefits in terms of reduction in non-CO2 emissions within the livestock system. But the other thing that we see in particular when we look at these scenarios with high livestock system productivity or livestock intensification is that we get a lot of indirect mitigation from land use change, right? So we're able to really free up additional land for carbon sequestration or for other sustainability-oriented goals like biodiversity protection. In fact, the indirect mitigation that we receive when we have healthier diets coupled with high livestock productivity outweigh the direct mitigation benefits that we see from livestock systems. This, however, is inconsistent with the results that we see in crop productivity growth. We were somewhat interested to see that productivity growth is in the crop production sector is not necessarily land sparing and can actually increase emissions or increase the amount of land devoted to crop production. And this happens really because increasing crop productivity growth in the US improves the US comparative advantage and raises crop rents, which has the effect of increasing production overall as the US becomes gains even more of an export share to the rest of the world. And that ultimately results in increased production emissions. Finally, and I didn't get into this much in the presentation, but happy to chat about it, global interactions really matter, right? So when we're thinking about domestic policies, be they direct climate policy incentives or indirect climate policy incentives, such as pursuing a healthier diet transition, we can't look at the US in isolation, or we can't have tunnel vision on our market and land use systems without thinking about broader connections to the international market through trade flows. What we assume about policies, what we assume about what's happening in the US has implications for the rest of the world, and we can't look at these systems in isolation. In conclusion, this is kind of the first of a series of studies that we're working on related to sustainable land use pathways in the US. We find that in particular, healthier diet and livestock system productivity growth can complement climate policy but our results are really inconclusive for crop productivity growth. And finally, our future work, what we're working on currently is exploring interactions between these healthier diet transitions and other direct environmental policy incentives, such as carbon pricing, such as land set-asides for biodiversity conservation. With that, thank you. And I'd like to acknowledge, of course, our funders from the National Science Foundation and partners at Sustainable Development Solutions Network, the FOLU Coalition, and ASSA. Thanks.
Thanks, Justin. There's one question chat too.
Okay. So Brian, great question. We're in the middle of thinking about that right now. We don't have a great solution yet, right? So, I mean, one way to do this would be to have different processing categories for these alternative meats or these kind of lab grown meats, which would sort of help you. I need to think about this carefully, right? I guess we would also need an alternative demand category there for these alternative protein sources. So it's something that we are thinking about, that we want to be able to do better in the context of an overall food system, but we're not there yet in this model. Do you consider separating feedlot finishing grass? Yes, we do. Yes, we do. We do. That's, again, something that we could probably improve upon. And, I think in general, one of the results that we find is that under these healthier diet transitions, you end up with a less intensive livestock system. So you're already kind of transitioning to grass-raised beef anyway. So even though you're relaxing extensive margin pressure and you're using less pasture land, you see a higher proportion of beef from pasture systems as opposed to feedlot finished systems.
Other questions?
Oops, sorry.
Okay. If not, we're going to move on then. We can come back to review the papers later. The next and the final speaker is going to be Richin. So Richin is I'm actually co-author of this paper. Richin is from Auburn. But I believe currently he's in California. Hope the weather is warm there at Berkeley for visiting for 6 months. And Richin, take over then.
Thank you, Hongli. So let me share my screen. I shared a screen a moment ago, but I couldn't find the unmute button, so I unshare it and find the unmute button. Okay. Good afternoon, everyone. It's my great pleasure to present this paper for you. My name is Richin Miao, as Hongli just mentioned, from Auburn. Currently is sabbatical at UC Berkeley. So this is the paper joined with Hongli, Feng, David Hennessy, Gaurav Arora, and Chuck Walsh. So this is an ongoing project, ongoing work. So any comments or suggestions are very welcome. So this paper is talking about the grassland easement acquisition. So we try to develop a integrated framework considering conversion hazard rate, additionality, and spatial spillover. So what motivated this work is the recent land use change in a prairie pothole region in the United States. If you're not quite familiar with this region, so it's depicted in the red area in this map. If we zoom into this area, you will see a lot of potholes in this region. So a lot of wetland plus grassland, which provide ideal habitat for millions of waterfowls in this area during the breeding season and nesting season. And however, so the grassland in this area has been facing a large pressure from agricultural use. If you look at the two maps from Yu et al. In 2018, you can see compared with the period of 1980 to 2005, the more recent period has much more land expansion, cropland expansion. That means mainly from grassland. If you compare this prairie whole region, so you'll see more green dots, which is cropland in this area. So the grassland is reducing, so at an increase in speed. So the grassland easement is considered as an efficient tool by the USFWS to conserve grassland. So it is a legal agreement signed with the government through the USFWS, and pays landowners a lump sum amount of land, but the land will be kept permanently under grass. So, but the landowner can still do grazing under land easement. So here's some a little bit more background about the grassland easement usage for the USFWS. So currently in this region, about 2 million acres of grassland is protected under grassland easement. And the goal is to protect even more, about 10 million acres in this region. So the issue is because of the crop price, the commodity price increased, and the land value increased, the average easement payment increased a lot in the past 2 decades. And so that requires more careful evaluation about easement evaluation and acquisition to improve the acquisition efficiency, to get more land protected under the limited amount of budget. So the research purpose of this paper is to develop an integrated framework to evaluate benefits and costs of easement acquisition, and also assess the consequences of different easement strategies in the presence of conversion probabilities, and how probabilities are affected by spatial spillovers. There's a lot of literature about conservation targeting and spatial spillover and so on, so I won't go into much detail about this, so I'll skip this one. And just to mention a little bit about our contribution. So in this paper, we focus on the spatial spillover effect on conversion probability. We try to model this and to consider this in an optimization framework. We'll also compare the outcome of different targeting mechanisms and heuristics acquisition strategies. So here is just an example to show you what we mean by spatial spillover effect on conversion probability. So the idea is, suppose in this example, we have 4 tracts of grassland. Grassland tract A, B, and C, they're close to each other enough, so we can call them neighbors. Tract D is far away from this 3, so you can call it as an isolated grassland tract. So the spatial spillover effect conversion probability is same. For example, for A, B, and C, if they're all maintained under grassland, their conversion probability to a cropland, a parcel of cropland, might be lower than, for example, when B or C are converted from grassland to cropland, then the probability of grassland tract A to be converted to cropland will be increasing, maybe because some externality impact or the learning impact from neighboring tracks and so on. So the spatial spillover effect will capture the conversion status of neighboring grassland tracts on the conversion probability of one specific grassland track. So we have a basic model or called general model in the paper. So we have a set of grassland to be protected. So we have a general setup. In this presentation, we'll skip that for the sake of time. And I will continue to use the 4-track example to show some mechanisms we analyzed in this paper. And later, I will show you a larger example using the actual grassland track in a county in North Dakota to illustrate the mechanism here. So the key elements we focus on in this study is additionality of benefits from easement, and also the spatial spillover effect on conversion probability. So again, by using the 4-track example, we put some numbers. We just put some purely hypothetical numbers on these 4 tracks. And their environmental benefit, their conversion probability, conditional on the status of other land tracts, and so on. And we consider the 3 benefit targeting mechanisms. One is the basic targeting. And so in this basic targeting, so the environmental benefits from eased land are viewed as the benefits secured by the easement. So basically, it ignores additionality and a spatial spillover effect. So this is the basic targeting. And we'll also consider an additionality targeting. So this additionality targeting improved the basic targeting, but it still ignores the spatial spillover effect. The third targeting is the additionality with spatial spillover targeting. So this is the most comprehensive or most preferred targeting for this, because it considers both additionality and a spatial spillover effect. And also we'll have some heuristics to look at how those heuristics algorithms will perform relative to this targeting optimization. So this is some parameters we put for the 4 tracks. For example, if you look at track A, so the environmental benefit per period provided is 0.6979. So this number is just a purely hypothetical. So just put those numbers there, and we'll solve the optimization problem based on different targeting strategies. And I want to bring your attention to this part, this column. So the conversion probability considering spatial spillover. So we know in the graph, the track A is neighbor of track B and C. So the conversion probability of parcel A will be determined by the land use status of parcel B and C. Okay? So here 0.3 means if both track B and track C are under grass, the land conversion probability for track A is 0.3. But if parcel B is under grass, parcel C is converted, then the conversion probability of track A is 0.4, and so on. So we have, so by doing this, we consider the spatial spillover effect. So to solve this optimization problem, so the easement manager's goal is to maximize the environmental benefit obtained from purchasing a grassland easement. He or she has a fixed amount of budget for each period. For each period, she can only purchase one parcel of land. So that's our simplified assumption. So the goal is to maximize the environmental benefit protected from grassland easement acquisition. So for the 4-track example, so we can solve the problem by using the backward induction and by drawing this decision tree. This figure just shows one branch, one major branch of the whole decision tree. The whole decision tree covers 4 branches like this. So we used the backward induction and solve the problem to identify so in period 1 which grassland tract should be acquired under easement, should be eased. Okay, so our results show that so after we do the backward induction solution, so we found that under the basic targeting, so basically this targeting strategy does not consider the additionality or the spatial spillover effect. So if the easement manager uses the basic targeting strategy, the tract A, grassland tract A should be eased in the very first period. If the additionality targeting is used, then the first tract to be eased should be tract D. If the additionality with spatial spillover targeting is used, then in the first period the optimal land tract to be eased is parcel B. Okay. So you can see under so the targeting strategy makes a difference. Under different targeting strategy, the grassland easement acquisition result is different. Okay. So by showing this, by this example, we're trying to show that if we consider additionality and further considering spatial spillover, so the grassland easement acquisition result can be different. So in the lower panel of this table, we show that the easement acquisition result under some heuristics. So the first one is a naive myopic algorithm. So in this algorithm, the easement manager will just pick up within among the available land parcels, they'll pick up the one that has the largest environmental benefit value, the one with the largest environmental benefit, without considering the conversion probability or spatial spillover effect. So under this heuristic algorithm, so in period 1, the optimal parcel to choose is tract A. We also consider the informed myopic algorithm. So in this algorithm, so the easement manager will consider the environmental benefit of a parcel and also the conversion probability. So basically, among the available land parcels to ease, the easement manager will choose the land tract with the largest value of the product between the environmental benefit and the conversion probability. So under this informed myopic algorithm, the optimal parcel to ease is parcel D. And under the third heuristic algorithm, So we call it spatially informed myopic algorithm, in which the easement manager considers the spatial spillover effect of the conversion probability. So in this case, the optimal parcel to ease is also parcel D in this specific example. So this is the a map showing the six actual land tracts in the Ransom County in North Dakota. So in a previous example, we just have 4 hypothetical grassland tracts. So we want to look at, so if we can apply our approach to some real world grassland tract. So we identify 6 grassland tracts in Ransom County in North Dakota. So this county is in the Western Corn Belt regions where the grassland to cropland conversion activity has been high. So we choose this 6 tracts. We have their acreage, we have their acreage information, and also the environmental benefit information. We use the duck pairs density of those grassland parcels to represent their environmental benefit value. So the first task of the analysis in this one is to estimate the conversion probability of this 6 grassland tracts. So we use the regression results from a recently published paper by Aurora and Hongli and David in GIM. So to estimate in that paper, the authors estimate the grassland conversion probability based on the grassland data or cropland, also cropland parcel data in North Dakota. So they estimate the conversion probability for some grassland parcels. So we use the results from that study and to predict the conversion probability for the 6 grassland parcels I just mentioned. So this is the regression they used in their study. So basically, so they use so here is the some independent variables they include the proportion of acreage under grass in the land tracts 500-meter outrange, and also some the proportion of acreage under easement in a tract 5-meter outrange, and some other variables, including land quality and distance to nearest highway and so on. So this is their regression results, the findings. We use the findings to predict the conversion probability of the 6 grassland tracts. So this is the prediction result. And based on their regression result, we can do some counterfactuals to see, hey, if so for tract A, what if tract B is converted to cropland? What if tract C is converted to cropland? Then what is the conversion probability of tract A under those scenarios? So for each tract here, A, B, C, D, we have 8 scenarios because each of them has 3 neighbors, and each neighboring tract has 2 status. So they'll have 8 kind of scenarios to consider. Okay. For these 2, they are neighboring tracts to each other, but they are not neighboring tracts for A, B, C. So in total, we have 6, and we have different scenarios. For the 6th tract, it's very difficult to solve solve the question manually. So we use a MATLAB toolbox called MDP toolbox, developed by Chad et al. 2014. And as I mentioned, the environmental benefit for those tracks are measured by duck pairs. The data from HAPIT US FWS. So we consider 4 scenarios. So based on whether or not we consider additionality or spatial spillover. So if we do not consider additionality nor spatial spillover, then we label it as no additional, no NA/NS, means no additionality, no spatial spillover. So we run we use the MATLAB toolbox to trying to identify the optimal grassland tract to ease at the first period under 4 different scenarios. We found that, so when we do not consider additionality or spatial spillover, so the optimal tract is C. If we consider spatial spillover but no additionality, it is still C. So overall, we found that whether or not to consider spatial spillover for this 6 tracts, it does not make a difference for the optimal land to ease. But considering the additionality make a difference. If no additionality is considered, so the optimal land to ease is parcel C. If we do consider additionality, the optimal choice will be D. Okay? So this is the result for the 6 tracts. So here's some conclusions based on what we have so far. So it is an ongoing work. We'll also include some, we're also thinking some future steps for this study. So here's just a brief summary of the findings. So the findings is considering additionality and spillover effect. So may generate different acquisition recommendation for the easement manager. And also we can see from the 4-track example, some heuristics can perform as good as the optimization targeting. And in the future, for the future steps, we would like to examine the additionality and spillover effect by using tracks from some different counties. So in our 6-track example, we used Ransom County in North Dakota. We have some other counties to study as well. So we also want to explore the performance of the heuristics based on the actual grassland parcels in those counties, not just the hypothetical example. Yeah, that's all what I have, and thank you very much for your attention. Thank you.
Thanks a lot, Richie. It's good timing. So that leaves us. Just for this one. Any questions just for this presentation before we open up for all of the presentations?
Just curious, why choose the? I'm sorry, I didn't raise my hand. Hongli, I'm very sorry.
Yeah, go ahead. Go ahead. Just
road protocol, but I was curious what motivated the choice of these 6 plots. And sorry if I missed that.
Yeah, that's basically because of the difficulty to do more tracks. So it has the curse of dimensionality for solving this optimization problem by using the MATLAB toolbox. So I tried to do 7 or 9, but it turns out it will take a huge amount of time to finish that. Yeah, so mainly because of the curse of dimensionality.
Okay. Any?
I have a question.
Go ahead.
So I guess I'm not thinking clearly about this, but if you have a spillover policy as an additionality and spillover policy, as opposed to just an additionality policy, does that tend to kind of spread out the optimal lands that you want in an easement, or does that, what kind of effect does that have in terms of the spatial allocation? I guess.
What do you mean spread
So-
out?
So does it increase the average distance? I guess if there's a spillover, it changes the probability of nearby parcels. And so depending on that change, it might make some parcels more additional and some less additional. So does that, like, you know, if you just had additionality as your criteria, you would just pick the parcels with the highest probability of conversion, I guess. But if you have spillovers, maybe it spreads it out, but I'm not sure, maybe it actually has an opposite effect.
Yeah, this is a great point. We didn't consider very much so far. I think so. If we do not consider the spatial spillover, which is as you mentioned, pick up the one with the largest additionality. If we consider spatial spillover, probably so the easement manager will prefer if you prefer a key parcel, if you will, a key parcel. That means if this parcel is converted, then other parcel conversion probably will increase a lot. So let's call it a key parcel. So among the among those neighboring counties. But in terms of spread out, because of the limitation of the analysis, we just study one tract per just at least one tract per period. We do not see the spread out effects after we consider spatial spillover. But I think if we allow a multiple tract to the east in one period time, so I can imagine if we consider the spatial spillover effect, so you will basically use some multiple key parcels, so that'd be more spread out around those available tracks, so that further conversion can be prevented by using those tracks. Great point. Thank you.
Thanks.
Other questions for Richard? If not, I think we just open the floor for questions and answers about all of the 4 presentations today.
I'll get the conversation going.
I do have sorry.
There you go.
A small comment for Andrew's work. So you mentioned, you didn't mention it so explicitly in your presentation, but I think additionality is also relevant to your CRP study, right? You mentioned if those parcels CRP offers are rejected, so if the continue stay in retirement or non-cropland use, so basically enroll them into CRP will not cause any additionality, right? So just just to bring this point out.
Yeah, I guess I think of it as additionality, like what we were doing. I hesitate to use the word just because it's it could lead to confusion in that context, because we're looking at proportions of different land uses, so there's not like it's not necessarily a binary situation where most
Right, I agree.
additionality is. But if you think of it as like proportion of cropland, then you can think of it as how much additional cropland would be retired if you expanded the program. But thank you, appreciate it.
I've been thinking about, Andrew, it's also for your presentation. I've been thinking about whether the impact, whether there are other ways to measure the impacts too. So one of your conclusion is about 1.2, 1.3 acres would be retired with additional $100. I'm not it's just the goal of the CRP. Acres, total acres is just one of the measure. And if, as you have shown, it's also well known that there's a very large regional difference because of the farmland cost. If you do it in the northern Great Plains versus in the central Corn Belt, the cost is going to be very different. So I'm not sure whether EBI would be a better measure too. EBI tends to be regional too, because each region will recognize their own environmental sensitive areas. Is that right? Yeah.
Yeah. So I'm gonna actually, if it's okay, I'll share screen.
Yeah. We have 8 minutes
Sure.
in total as a panel.
Okay, I'll just talk then. We do have the information about the EBI, so that's definitely something we can look at. In the current slide, we do look at average EBI scores across the different states, so we can just kind of visually compare how EBI compares to the kind of acreage per $100. But we could think about different ways of combining those into one metric. It's kind of tough to think about, but yeah, if you get an additional EBI score weighted by acreage or something like that, it'd be interesting to look at that. Thanks. Yeah.
Yeah.
I'll stay on Andrew, since we're talking about your paper. So one of the objectives was cost of avoiding land use, right? Estimation of cost of avoiding land use. And to estimate that, you used rejected bids. What's the motivation for that? Why not use the accepted bids? Could that be?
So the reason is that we have information about both counterfactuals from the rejected. So it's because we can observe what they actually ended up doing and then what they proposed to do. It's kind of like, if the program was a little bit bigger in 2016, what would it have obtained in terms of land use, and what would the cost have been, because we know what the rental rate that they proposed was. So it's not necessarily the case that these land use impacts carry over to the parcels that actually enrolled in that particular sign up. But because it was a sign up with a lot of rejected offers, you might be able to argue that some of those offers would have been accepted in another sign up. And so at least for some portion of them, they're kind of in the ballpark of what a normal sign up would be obtaining in terms of avoided land uses. Is that kind of addressing?
Yeah, kind of. I was just wondering if the estimate of cost of avoidance would have been, how different would it be theoretically, if you actually used enrolled rather than rejected?
So we do, yeah. I mean, I showed that slide. We look at how that varies across EBI points, and so I guess part of the idea of doing that is, if we can't observe the land use of the people that were actually accepted, but if we looked a little bit higher in terms of EBI points, maybe there's a trend. What we do find is through that for the 3 highest quartiles, there's not a ton of difference in the cost per land use retired. So maybe you could say extrapolating a little bit up, it's going to be similar. If you get to the really high EBI scores, you might be a little more hesitant to do it. But it tells you at least a little bit about that portion of the population.
I'm going to spread the conversation a little bit. So I actually have one question for each Justin and Levin's papers. So Justin, I think for your research, it's obviously it's a very relevant question. You know, suppose the society does change diet. Suppose your lab meat does become more widely adopted. What are the land uses? And it's just it's so interesting for you to tackle that. But if in terms of doing research, how do you control? I mean, how do you model how fast our society will start transitioning towards a healthier diet?
It's a great question.
Yeah.
Oh, sorry.
No, that's it. Yeah.
Yeah, so it's a great question. Thank you. The analysis that we use is pretty simple in nature, in that we're taking kind of a national demand schedule, right? So we have projected demand, we have demand growth and kind of preferences that change with income and vary across these broad socioeconomic scenarios. And what we're doing specifically with the healthy diets is we're just using simple demand shifters. So there's sort of national shifters which reduce the demand proportionately of these different products that go into these kind of food categories like red meats, pulses, poultry, pork, etc. So that's the way we're doing it, is just some simple demand shifters right now. We've been thinking about this a little bit more in the context of how do we regionalize this to take advantage of emerging policy incentives, nudges that are supporting healthier diet transitions at more of a local scale, either through taxes or through other behavioral incentives to encourage the adoption of healthier diets. So how do we localize an analysis like this to look at a healthier diet transition, say in California or in parts of the Northeast, consistent with, I guess, more progressive policies on diets that might exist in those regions. So that's longer term. We're not there yet. Right now, we're using a pretty simple approach.
Yeah, I think so. Yeah.
I had the same question for Justin, actually. And I'm familiar with this partial equilibrium model. So there's demand curves for categories of commodities, right? There's no demand curve for like a burger, right? But the diets, the healthy diets, the guidelines are something like reduce, I don't know, less fatty foods or whatever. How do you translate those into commodity demands? How do you shift the demands? Like a demand for corn.
Okay. So that's where it gets a little bit complicated, because we have to do things like, there's general guidelines for sugar intake as a proportion of your diet, right? Well, sugar can come from a lot of different commodities, including high fructose corn syrup. And so what we did is we have like a baseline proportion of each of these sort of specific commodity groups to the aggregate category, in this case, sugar, right? And so we're shifting the demand for corn based on a proportionate change in the demand for high fructose corn syrup, consistent with this overarching categorical shift in demand for sugar as part of the diets, right? So we tried to be pretty methodical with this and go commodity by commodity. And so for commodities like corn, it's difficult because they go into so many different kind of aggregate food categories. Soybeans are the same way, obviously. Soybeans are really interesting, right? Because they can be a source of alternative proteins, but they're also a major source of oil seeds. And so you have this kind of push and pull whenever you shift to a healthier diet. It's
very interesting. Yeah. So Yes, so for Levin, I think the paper that I think has kind of raised in some questions. I thought the interaction between EOG and water and public energy to less extent, especially water, will affect how EOG affects ag land use. And I heard that fracking is actually quite water intensive, isn't it? Yeah, so.
It is, but water, if you compare water use for fracking versus water use in agriculture, it's not even close. I mean, what it takes to frack a well is about the same amount of water as it takes to plant, I don't know, 5 acres of corn. So it's really not comparable. In some areas, they may use, produced water to irrigate, but it's not going to really make that much difference. I mean, produced water is about 10% of what we inject, and what we inject is equivalent to about, I don't know, 5 acres of corn. It's really not.
Okay. Yeah.
But if technology-wise, if you look at California, there a lot of drilling, the deep drilling and fracturing. There they use this technology to extract water from aquifer. Not oil and gas. In that respect, those drilling teams that are involved in this, many of them are contracted to drill wells, not for oil and gas, but to drill wells for water. In that respect, there might be this spillover. If there is more oil and wells being drilled for oil and gas, then maybe there are these teams who are also available to drill for water. And that could happen. Yeah. And we did not model that kind of thing.
Just a basic question that I don't know. So in a region where the development of local EOG affects the local OG price, oil and gas price, like for example, in the Appalachian region, or maybe or in the other region where it gets slightly lower oil and natural gas price, or no? I'm just very basic question.
Well, prices regionally are affected by many things, right? And in Appalachian case, for the longest time, the limiting factor was the shipment. The pipelines were, the capacity was limited. They couldn't ship the oil and gas, or gas really in our case. They couldn't ship gas out, so that kept the prices really down. And so there is this difference, but there's factors. There's a capacity factor, a shipment, pipeline capacity factor that affects the price. Typically in agriculture, it's what we need: electricity, energy, right? So we don't use gas directly, or oil. Well, gasoline, I guess we use, but we need energy in the form of electricity. So I don't know if that answered your question.
Yeah, that let me learn a bit. Yeah, I don't know the topic. It's good for me to learn basically in order to understand your model. The other, I know, I think you're free to go now, but we're free to discuss more. If you have something to leave, then feel free to leave. So the other thing is the climate is always a bit tricky to model land use. So did you use annual climate, or annual weather, or did you use a kind of average climate in your modeling? Or if you use the annual weather, did you use lag?
Oh, I use the annual precipitation, annual average precipitation over monthly.
Yeah, did you try to use it, at least if you use that? Because when people think about whether to grow, especially if you're talking about, I think you group agriculture together.
Yeah.
I think maybe climate matters more than just the annual weather variation. They understand, farmers understand maybe next year will be dry, next year will be wet, but it's the average weather when they make decisions whether I'm going to go to expand my cropland or pasture land.
Yes, because we use the aggregate crop acreage. So the acreage include 8 crops. So something like corn crop, it is usually in corn crop acreage, corn acreage literature, they use like precipitation in March or April to be the climate variable, right? But we also have other crops such as sorghum, soybean, barley. They may not plant in June, so they may plant in October, something like that. So that's why I use the average annual climate variables here.
It's a climate, it's not.
Yeah.
Yeah, okay, yeah. That probably makes more sense than annual weather. Yeah.
Yeah.
Yeah, exactly. Okay. Other topics, other questions? If not, I guess thanks everybody for coming, and it's a very interesting presentation. Thank you very much, Levin, for putting this session together.
Thank you, everybody, for agreeing to be part of this, and to you, Hongli, for volunteering to be the chair discussant.
You know,
you.
there are other opportunities. Oftentimes, co-sessions together. If we do, I know I'll continue to do non-research related research. I think it doesn't prevent us from organizing similar sessions at other venues. I think we should keep that in mind. AERE sometimes call it for. No, this is AAEA, but sometimes AERE calls for sessions or otherwise. I mean, I'll be glad to participate. Yeah, or sometimes if I do organize like Levin does, I hope you will respond to me too.
Absolutely.
Of course, anytime.
Yeah, I know we will all. Our research will evolve to a slightly different topic. That's the whole point. Like, let's keep the communication going, keep the interactions going. Okay.
All right. Thanks, everyone. Great session.
Yeah.
Thank you.
With that, I'm the host. I'm gonna end the meeting for all. Okay.
Thank you.
Bye.